All right. All right, so here we go. We're going to take some notes today. I'm not ready to hand those texts back just yet. The scores are in. Got a couple. Just take it still. We're going to take some notes. We're going to talk about vectors now. Chapter 6 is about applying trigonometry in different situations. So it's basically split into two chunks. Some vector work and then some work in polar coordinates. I think you'll find all of it very fascinating. But it's got its own language, so we got to make sure we know the words that we're talking about. So what is a vector? A vector is a directed line segment. It is a directed line segment. So what that means is that a vector has direction and length, because it's a segment, but it's a segment pointed in a specific direction. So our vector notation is generally like this. So it's a little one-tipped arrow to indicate, well, you tell me, why don't I write it like this? That's array, and what does array do? Goes on forever and ever. So if this is point A and this is point B, then this would be vector AB from A to B. That's the notation that we use. It is a directed line segment. Okay, so next, a position vector. Now, vectors can be drawn anywhere. Okay, so if I talk about a vector, like if I use this kind of notation to talk about a vector, which is very common, the problem is, if that's all you've got, you don't really know where it is, right? So we typically standardize it by calling any, or by, if they don't give you specific points, like if they don't give you an A and a B, then you are assuming this is a position vector, which means it begins at the origin. It's in standard position. It begins at the origin. Now, there will be times, especially here in the beginning, where I'm giving you points, A, B, C, D, whatever. When that's the case, then of course you draw it wherever points A, B, C, D are. But if I don't give you the points, then you're going to draw it as a position vector. Okay. Now, I think for the next one, it might be easier, for the next definition, it might be easier just to come down and do problem number 1 that says point A is 1, 3, and B is 2, 4, and we're going to find the coordinates or the components of vector AB. So in other words, we're going to write it as a directed distance, okay? How that's done, these are the components right here, X and Y. X and Y are your components, or your coordinates of your vector. So vector components are the X and the Y that describe the vector's movement and length. So I want you to think about this for a minute. This vector is going in the X direction from 1 to 2. So his X component is positive 1. He went from 1 to 2. But what about his Y coordinate, or his Y component? It's from 3 to negative 4. So what's that? Negative 7. So that vector moves 1 unit in the X direction and negative 7 units in the Y direction. Okay? Now, so vector components are simply the X and the Y. They're linked to sine and cosine because X and Y are linked to sine and cosine. We'll talk about that later. Magnitude. Magnitude is the vector word for, anybody know? Length. It's the vector word for length. So when someone asks you to find the magnitude of a vector, you're just finding its length. So let's talk about this guy right here. he has components 1, -7. So if I drew him as a position vector, it would look like this. Now I know what you're thinking, but wait, Mrs. Ford, you gave me a point A and you gave me a point B, so shouldn't this vector be sitting somewhere else? Would that change it if I put it somewhere else? What makes a vector unique is its direction and its length. So I can put this anywhere I want. If you'd rather plot the point 1, 3 and 2, -4 and draw the vector like that, that's okay, but that is exactly the same vector as that one because it has exactly the same direction and exactly the same length, wherever you put it. So it's easier just to make it a position vector. Okay, how long is it? Easy. It's the square, Pythagorean theorem. It's the square root of 50, which as Seth said is 5, square root of 2.
That's not always part of the 90-degree angle.
Well, if you're plotting the point 1, -7, aren't you going over and down or over and up or something? Yep, X and Y are perpendicular always. So let's talk about, first of all, notation. The absolute, excuse me, the absolute value notation is how we describe magnitude. And that makes sense to you because when you were a freshman in Algebra 1 and you talked about absolute value, the absolute value of a number was its distance from 0 on the number line, right? So what do we got here? The absolute value of that vector is its distance from the origin in the coordinate plane. That's the absolute value. We call it magnitude. This is the notation for the magnitude of the vector. How did I do that? Or how did he do it? How did he find the magnitude? Real simple. Didn't he just square that and square that? And add them up? And take the square root. We're never going to be confused about magnitude. Square the first one, square the second one, add them up and take the square root. The 0 or the null vector is the vector whose coordinates are 0, 0. Now this is one of those technical math points. That is really not a point. It's a vector. But it's a vector whose magnitude is 0. So when you draw it, it looks like a point because it has its magnitude is 0, but I kind of like to think of it as a little atom, ATOM, that has no, it's just this little thing that's kind of bouncing around. This guy has no magnitude, but he has whatever direction I want him to have. It's kind of weird. But we need the 0 vector in some of our operations. In a vector, like when I drew this one right here, this was vector AB. This is called the initial point, and this is called the terminal point. That vocabulary should not be confusing for you. What does initial mean? First or beginning. And what does terminal mean? End. So if we have the vector AB, point A is the initial point, and B is the terminal point. Equivalent vectors. Any idea what equivalent vectors might be? Alana?
Vectors with the same magnitude?
Actually, equivalent vectors will have the same magnitude, but there are vectors can have the same magnitude and not be equivalent.
Same direction.
Same directed distance. That's exactly right. So if they're equivalent, Alana, they have to have exactly the same vector coordinates. Because, let's talk about that, just make sure you're clear on it. Would the vector 7, 1, Alana, have the same magnitude as my AB? Would this vector have the same magnitude? But it's clearly in a totally different direction, right? So, in order to be equivalent, you must have the same direction and the same magnitude. In other words, the same directed distance. Anybody know what a scalar is? You've probably heard that word, especially if you've done any physics or maybe science stuff at all, what a scalar is. What's a scalar, Joseph?
Is it a segment without it's either, I don't know, forget.
Well, you're kind of going in the right direction. A scalar in vector land is just a real number. It's just a real number. So there's a difference between this and this. That is a scalar. It's just a number, like a coefficient or something. It's just a number. This has direction and magnitude. So a scalar has magnitude, I guess that's 3, but it does not have any direction at all. So scalar, we're not going to be confused by the vocabulary because we're going to use it with our matrices too. Vectors and matrices have the same language. A scalar is just a real number. Resultant. Anybody know what the resultant is? The resultant is the sum of 2 or more vectors. So instead of saying find the sum, in vector land we have to say find the resultant. But a resultant is nothing more than a sum. So we're not going to be confused. We're going to learn how to add vectors together. And that's what we do when it says find the resultant. Unit vector. You know this one. Guess it. Guess. What's a unit vector? What's a unit circle? The one we use all the time. It's centered at the origin and has a radius of 1. A unit vector is any vector whose length is 1. It's 1 unit long. It's a unit vector. Is this guy a unit vector? No, because his magnitude is 5√2. Right? How do you know if something's a unit vector? You find its magnitude. If its magnitude is 1, it's a unit vector. Now, the standard unit vectors. Okay, let's talk about those. The standard unit vectors have special names. They are called I and J, and you gotta be careful because we also use I for the imaginary unit, but this is different. Here's my coordinate plane. Here's the origin. I'm gonna pop over 1 step. This is the vector I, the unit vector I. It has a length of 1, which means this point is 1, 0. And the coordinates of that vector are 1, 0. It goes right 1 and up 9. That's one of them. The other standard unit vector is this one. We call him J. What do you think the coordinates of J are? 0, 1. Those are the standard unit vectors. Every vector in 2 dimensions can be written as a linear combination of I and J. So let me say that again. Every vector in 2 dimensions, including this one that I drew a little bit ago that I just erased, my vector AB, can be written as a linear combination of I and J. Now what that means is, let's look at our vector AB. AB goes exactly 1 unit to the right. So 1 unit to the right is I. So it is 1I or just I. But then it goes -7 in the vertical direction. So that's -7 J's. I minus 7J means 1 step in the horizontal direction and -7 steps in the vertical direction. And that's what this vector did, right? Every vector can be written that way. So what would this one be? Let's say this is vector B. What would he be in terms of I and J? 7 I's and 1 J, or just plain J, you don't need to put the 1 in there. It's real easy. The language sounds hideous. This is a linear combination of I and J. It's easy. Whatever your first coordinate is, that many I's and that many J's. Every time. Okay, and the direction angle. When you draw a vector in standard position, this is its direction angle. It's the angle it makes with the positive x-axis. Normally, those direction angles are defined between 0 and 2 pi. You are used to that, right? You're used to that. So we would have to get this vector, we would have to go all the way around. Now, would this also be a possibility? Yes, but almost always you're expected to do it this way. So we're going to use the positive one. So what's the direction angle? The angle the vector makes with the positive x-axis. The angle it makes with the positive x-axis. Okay, boy, got all our vocab, or at least all of it so far. We have a few more weird words to learn, but that's it to get us started. So let's look at problem 2. Given these points, now these are points, these are not vectors. So R and S and P and Q. We are to determine if vector RS is equivalent to PQ. So we're going to figure out if they're equal or not. So what do you think we're going to do? Find the vector components, that's exactly right. What are the coordinates or the components of RS? You're going from -2 to -1. 3. And from 2 to 6. Perfect. Now, what about from P to Q? We're going from 2 to 5. And from -1 to 3. Are they equivalent? Yes, because they have exactly the same direction and exactly the same magnitude. That means they are equivalent vectors. If they hadn't matched, then the answer would be no. Easy enough? Yep, that's all you have to do. David?
How do you know if it's the same direction?
Right 3 up 4. Right 3 up 4. Right? Okay. Now the next one, they give you the vector. So point C, this is a point. And the coordinates of the vector are -3, 6. And your job is to find point H. Now, you've been around me long enough, I have to draw everything. So I've got a vector out there. CH. I know it starts at 3, 5. And I know it travels -3, 6. Those are the coordinates of the vector. So I'm going to start at 3 and move -3. So where am I going to end up? 0. And I'm going to start at 5 and move 6. So where am I going to end up? 11. There it is. That's point H. The vector tells me how I move and how far I move. Number 4 is the same problem, except I have vector RS, and I know where I end, and I know how I move, but I don't know where I started. you see the difference on those problems? Okay, so now we gotta kind of think backwards a little bit. Where did we have to start so that if we traveled positive 2, we'd end up at 4? 2. And where do we have to start so that if we back up 4, we end up at negative 3? There you go, you got it. Easy, easy, easy. What's number 5 asking me to find? The magnitude, absolutely. So, can you find the coordinates of the vector? What are the coordinates of AB? Did somebody say negative 2? I didn't hear the end of it. Okay, would we all agree with that? If you can't do that, we're in trouble because you have to do that in a lot of problems. That's kind of the beginning. All right, so you got that. Good. Now, what does this mean? Magnitude. And magnitude, we said we're going to square the first one, square the second one, add them together and take the square root. And if you are confused by that, remember that vector goes left 2 and down 6. So left 2 and down 6. Wouldn't we do the Pythagorean theorem to find its magnitude? Square, square, add them up and square root it. What else could you have done in this problem? Could you just use your distance formula on the original 2 points? Would that have worked? Absolutely. So if you want to do that, you surely, surely can. All right, you happy people, last period of the day on a Friday?
Yeah.
Oh, I don't know why this always happens to me. I always teach the last period of the day.
That's good.
Well, except for people like, look at Clayton, he's like. All right, here we go, number 6. Everybody's keeping up so far. Here we go, number 6. We've got a couple of vectors now. You really have to pay attention to the way the problem's written. This is a vector. This is not a point. This is a vector. And so is this. And so is this. And we're going to find the resultant of U and V. In other words, we're going to add them together. We're going to find the resultant of U and V. David?
Why aren't we like going along in the notes?
I thought we were.
We are. You know?
Oh, Lord.
I was looking for number 1. Well, that's the homework.
Okay, U plus V. If you were absolutely clueless about everything, you could guess this answer. How do you think we're going to add these 2 vectors given their coordinates? Alana?
Negative 1 plus 4 and then 3 plus 7.
Exactly. That is all there is to it. Now, sometimes we don't have vectors written this exact way and things are a bit more complicated. But as long as you have their coordinates, you just add x and x and y and y and that's it. This is called the resultant. All right, 3u. Again, well, first of all, let's make sure we're clear our vocabulary. This is a scalar, right? That's just a number. So we are going to multiply 3 times u. And again, you can guess it. It's obvious. 3 times u is going to be what? Negative 39. You like distribute it. It's that simple. Now, I do want to point something out here, though. This vector is in exactly the same direction as the original one. I mean, think about slope for a minute. If you go left 1, up 3, isn't that the same direction as left 3 up 9? So these vectors are exactly the same direction, but this one's 3 times as long. 4v minus u.
That's W.
Or w. Thank you. 4v minus w. Okay, here we go. What's 4v? We just talked about it. What's 4v? 1628. And now I'm going to subtract w. What do you think that answer is going to be? 1622. Oh my gosh. Oh, Mrs. Ford, this is so easy. You're right. Okay, what about D? All right, got some couple steps here to do. So we're going to take u, which is -1, 3, and we're going to add it to 2v, which is 814. So we're going to add these, and what do we get when we add them? 17. So this is u, this is u plus 2v right here. But I want its magnitude. So how do we do that again? Square them both, so 49 plus 289. At some point I had to memorize these, but I was like
We should do that.
5th grade. That's been a while ago. Yeah, 289. And then add them together and we get 338. And that is actually 13 root 2. That's incredible. Is that right? Yeah, because 338 divided by 2 is 169. There we go. Everybody still with me, okay? Enjoying knowing what's going on? Just wait, I'll ruin that in a bit. Okay. A unit vector in the direction of u. Now, your job is to find a unit vector in the direction of u. If I drew u, would you agree it would look like this? That would be a picture of u. Okay. How long is u? Square root of 10. In other words, u is not a unit vector. Because a unit vector has to have a length of 1. So what I want to do is take that triangle right there, and I want to shrink it so that this length is 1. So I'm going to divide every side of the triangle by root 10. Will that make the length now 1? Will it keep the direction the same? In other words, is the ratio of the sides the same? The slope is the same. So what are the coordinates of my unit vector? My unit vector, this was u, and we got to pull a little u down here to indicate the unit vector for vector u would have an x of -1 over root 10 and a y of 3 over root 10. Now this is one of those times where you don't have to rationalize if you don't want to. We're kind of done rationalizing. So how did I do that? How do I make a vector into a unit vector? Real simple. I just divide it by its magnitude, right? And that gives me a length of 1. Write v as a linear combination. Oh wait, okay, David, I skipped f accidentally, but I'll get it, okay? I'm on G now. I'm writing V as a linear combination of I and J. We talked about that, real easy. Here's V, what's it look like in terms of I's and J's? 4 I's plus 7 J's. It can't be any easier, that's it. That's all there is to it. That's a linear combination of I and J. This tells me, remember, I is horizontal steps and J is vertical steps. So this says I'm gonna go 4 horizontal steps and 7 vertical steps, and that's exactly what this vector's doing. Now, I need the direction of vector U. So vector U looked like this again. This was U. And this is its direction. The direction angle, the direction of the vector, is, where is it relative to the positive x-axis? So anybody have an idea on how we might find the direction angle? Alana?
I actually have a question because that are like for our graphs, is like the graph gonna be like in radians?
Well, graphing it, I mean, the xy coordinate plane, that has nothing to do with radians or degrees. But when I answer this question, I could answer it either in degrees or radians. And normally, the directions are 0 to 2 pi, which would tell me to be in radians. But for fun, we'll go ahead and answer this one also in degrees, just to make sure we can do both. But yes, you could answer either way. The directions usually tell you, but if they don't, then either one is fine, okay? Okay, so, and how am I gonna do this? All right, I know, if I draw my little right triangle here, I know that this is -1 and this is 3. Agreed? So that angle right there, I could find by doing second tangent. Now, I like to leave the negative out. You don't have to. Second tangent, 3. And this angle in degrees is 71.57. I'll do it in radians in a second. My calculator set degrees. So what would the direction angle be though? Please don't say 71. What is it? 180 minus that? So in degrees, it would be 108.43. And then I can do the same thing in radians, just change my calculator to radians, and do second tangent 3. So in radians, it's 1.25 for the reference angle. How would I find the actual direction then? Pi, from pi, right, subtract it from pi. And in radians, it would be 1.89. So remember, just like always, your calculator only gives you the reference angle. You have to make adjustments depending on which quadrant you are in, right? That's what we've done all along. Everybody okay? The radian measure, 1.25 is the radian measure of the reference angle. So my calculator set radians, I type second tangent 3, and that's what it says. So then I subtract that from pi to get my second quadrant angle.
What, how do you get the 189? Like, what do you subtract?
From pi? Pi minus 1.25?
By pi, like 3.14, right?
Yes, but I use my pi button, yeah. All right, number 7, find the coordinates or the components of a vector with magnitude 7 and a direction angle of 115. draw this guy. He has a magnitude of 7 and a direction angle of 115. Does that make sense to everybody? And what am I looking for? I'm looking for the components. Aren't I looking for X and Y? I want to be able to write this vector as like this. So I need to figure out what the X and the Y are. Do you know how to do this? Yes, you do. You know how to do this. Yeah. How big is this angle right here? 65. So can I say, for example, cosine 65 equals x over 7? And sine 65 equals y over 7? So then I'll type into my calculator, I'm solving for x and y. So I'll type 7 cosine 65 and 7 sine 65. Does this make sense to you in terms of stuff we've already done, really? Now, those are degree measures, by the way, so I've got to change that calculator back to degrees. And 7 sine 65 is 6.34. Sine goes with y. Always and forever, sine goes with y. And 7 cosine 65 is 2.96. Are those the numbers you got? Are they the right numbers? They'll make that guy negative, right? Why do I need to make that guy negative? Because that angle is in quadrant 2. Wait, don't turn the page just yet. I'm going to show you something now.
Like if you wanted to, could you do like sine and cosine 25?
Why 25? Oh, well, so you would take say the sine of 25 equals x over 7? You could. I don't know why you would ever do that, but you could if we give you the same result. But here's what I want to show you. The original direction angle was 115. What if, instead of finding the reference angle, what if I just used 115? So instead of doing 7 cosine 65, what if I did 7 cosine 115? Try it. What happens? You get the negative. You don't have to artificially make it negative. It comes out negative. And what if we did 7 sine 115? You get exactly the same thing. So what I am trying to impress upon you is that you actually don't have to go to quite as much work as we did. If you know the magnitude is 7, and you know the direction is 115, x will always be magnitude times cosine of direction angle, and y will always be magnitude times sine of direction angle. So you don't even need to draw it. Now, if you do, if that makes more sense to you, because that's what we've done before, it's perfectly okay. But if you do this, then you have to make sure you're including any negatives. If you do this, the negatives come out automatically. So to find the vector coordinates, magnitude times cosine, magnitude times sine, every time. Easy, easy, easy. All right, now you can turn the page. Here's where things get a little bit hairy. It's easy, but we have to make sure we're staying alert. A plane is flying on a bearing of 65 degrees, okay? This is a navigational problem. So 65 degrees would look like this. Remember, when we're doing navigation, we're starting from due north. At a speed of 500 miles an hour. So the magnitude of the vector is 500. The speed gives us a distance, right? So in 1 hour, he goes 500 miles. The speed does not tell me where he's flying. Speed is a scalar. Speed is just a number. So the magnitude of that vector is 500. And I want to find the components of that vector. Okay, we just talked about it. The components are the x and the y, right? And I just got done saying that you can do this with the given angle, but only if it's a direction angle. Is 65 a direction angle? No, because it's measured against the y-axis and not the x-axis. So in this case, you must find this because that's the direction angle for the vector. It's kind of confusing because we got to follow the math rules, which means measure it in standard position, but we're doing a navigational problem. So, 25, is that right? Yep. So what's x? X will be 500 cosine 25, and y will be 500 sine 25. Am I going to have to change any signs, SIGNs?
No.
Nope. Because I am sitting right there in quadrant 1. So y is 211.31 and x is 453.15. What do the components tell me about this airplane? I know my airplane is flying on a course of 65 degrees for 500 miles. What do these two numbers tell me? David?
It's height, and then how far away it is.
Well, it tells me how far east I've gone and how far north I've gone, right? I've gone this far east and this far north. So it gives me the components, the east and north components. All right, would you try number 9? It is the same exact problem with different numbers. So would you try number 9 by yourself? Yeah.
I was just looking at something.
You were looking at something on your iPad?
Yeah,
Okay. You don't do that.
yeah.
I thought I would make it through the day without an infraction. Nope. Who got answers? Who's willing to share? Alana?
For X, I got 79.89, and then for Y, I got 453.01.
All right, who wants to agree or disagree with that? Charles?
I want to disagree only on the Y coordinate because she didn't have a negative on the Y.
Yep, aren't we down there in quadrant 4?
Yeah.
So,
I used the original formula, but it didn't put a negative on it.
okay, but remember, you mean you use the 170 or something?
Like, I used the, oh, we're supposed to use the one, oh, okay.
No, you don't have to use the 170. In fact, you shouldn't use the 170 because when you draw a course of 170, it's down here like this, right? This is where 170 is. So 170 is not the angle you're making with the x-axis. The angle you're making with the x-axis is 80.
Yeah, I used 80, okay, so I would get a negative if I used 170.
Well, you don't use 170, okay? Don't use 170. You're using 80, but you're recognizing that in this quadrant where your airplane is, x is positive and y is negative. Okay?
Why don't you use the, like, all the way around?
Well, you can, but I'm solving this triangle. So if somebody said to me, okay, Lisa, what is the direction angle for this airplane? This would be the direction angle for the airplane. Okay? And you can use that if you want to.
So it's the same?
Yes. But if you use, what would that be, 280 or no?
Yeah.
Yeah, if you use 280, it will actually come out with the negative. That's my caution to you though, is the 170 is not a direction angle, it's a navigational angle.
So if you use 280, it comes out negative?
Uh-huh, yeah, the sine does, the y does, yeah. The cosine will stay positive. All right, we're gonna do one more. This one's gonna perplex you maybe, let's see. Number 10, last one. So, pilots leave in San Francisco flying, okay. She's supposed to be flying due east. Okay, this is the way we want her to fly, okay? So this is gonna be like our resultant right there. We want her to end up flying due east. The problem is, there's a wind with a bearing of 60 degrees. So here's the wind. No, 65 miles an hour, okay. And we want to find how she should go, assuming that its speed with no wind is 450. So, think about this for a second. If she wants to end up flying due east, if her destination is due east, but there's this wind blowing, she can't go due east, right? Because the wind is going to push her off course. So where should she be flying, just generally speaking? Shouldn't she be flying down here? Because we need the wind, see the wind is going this way, so won't that push her back up to where she wants to be? Don't let this arrow confuse you. It's a 60-degree angle. So think about it, the wind is blowing this way. So think about this wind blowing at her from that direction. Isn't that gonna push her up? Now all I know about that vector is that her speed, her airspeed is 450. Now that isn't her ground speed because that wind's going to change that. But that's 450 and I have no idea how big this angle is. I'll call it theta. But I do know, this is the wind, this is the plane. I do know that if I add the wind plus the plane vector, the wind vector and the plane vector, I want to end up with the end result vector. Would you agree with that? So when I put these two vectors together, I want to end up with this one right here. What are the components of the wind? You can do that for me. What are the components of the wind? What's the X for the wind? Won't the X for the wind be 65 cosine 30?
56.2.
So this is, and the Y will be 65 sine 30? Does that make sense to everybody? So these are the components of the wind. All right, what are the components of the plane? Well, I don't know the angle, but can I say 450 cosine theta and 450 sine theta? Because I don't know that angle, right? That's what I'm trying to figure out. Now, wait a second. I want this plane to end up right here. I really don't know anything about my X, but what do I know about my Y right there? This is where I want the plane to end up. What do I know about the Y there? What's the Y for that point? 0. I'm going due east, so don't I want my Y to be 0? Hey, don't just stare at me. Think about it. I'm on the x-axis. Isn't y 0? That means that if I add my y's together, I have to get 0. Remember, when I add vectors, I add the x's and I add the y's. So when I add these two y's together, I have to get 0. Wow, that's a crazy equation. All right, let's see, 65 sine 30, what is that? 30, well, 450 sine theta equals negative 65 sine 30. Agreed? And so sine theta equals that over 450. Shoot, I know how to type that in. What do I have to do to get that into my calculator? Inverse sine. So second sine, inverse sine, negative 65 sine 30 divided by 450. I'm in degrees and I got negative 4.14 degrees. Does that make sense, just logically? We want him flying down there, right? We want that angle to be negative. Now, the question though was, determine the compass heading, so I'm going to do that in a second, and the plane's, the airplane's ground speed. So in other words, how far has it actually gone? What is this length right here? This is 1 hour, 65 miles in 1 hour. This was 450 miles in 1 hour. This is going to be how many miles in 1 hour? Well, can I find X now? Isn't X the sum of 65 cosine 30 and 450 cosine theta, which is negative 4.14? on my calculator. Remember, this is how far the plane's gonna actually go in 1 hour. This is how much ground he's gonna cover in 1 hour. So to get the x, I'm gonna add my x's together. And I now know this angle, so I'll be able to do that. Let's use our answer button. So 65 cosine 30 plus 450 cosine second answer. I got 505.12 miles per hour. Now I've answered everything except I haven't actually given the plane's heading yet. So the plane's heading, remember, bearing measured from due north, right here. What's that gonna be? 94.14. So this plane needs to fly on a heading of 94.14
That makes that in degrees.
degrees, because this is in degrees. And the actual ground, the actual distance covered will be 505 miles. Since the wind is blowing this way, it's kind of pushing her. It's blowing her off course, but it's also pushing her a little bit. All right, that's enough for one day.